Where does inspiration come from? It's a question artists and scientists have been quietly asking for centuries. Ask an artist, and they'll talk about curiosity, observation, daily rhythms, and the details suddenly feel bigger than they should. Now, ask a mathematician or a physicist, and they'll often say the same thing. At its core, inspiration is pattern recognition. It's noticing when the world reveals a structure that feels purposeful. Now, that can look like a swirl of cream in your coffee that looks like a spiraling galaxy, or cracks in the dry mud that echo stress patterns inside neutron stars. Both art and physics are attempts to decode those patterns and to make sense of why the universe looks the way it does. So, today we're going to follow those patterns, whether that's Renaissance sketches, black holes, and from sacred geometry to gravitational waves. I'm your host, Autumn Fanav, and I am joined by Dr. Ronald Gamble, an artist, co host of the popular podcast Science Will Win, a theoretical physicist at NASA, and a research scientist at the University of Maryland College Park. Ron, welcome to the show.
Thanks for having me.
Thank you for coming on the show. Now, I'm curious, where did your intersection of math and physics and art come into play? Tell us a little about your experience and your journey with this.
Basically, I was a child, right? So my mom, she painted, she drew. My dad also drew some, but she was also like a kind of like a sci-fi nerd as well. So I grew up watching Bob Ross in the morning, and then we watched Star Trek, Star Wars, First Contact, like all of
All
that
the
kind of
good
like towards
stuff.
the evening. Yeah, like all of the super lore, the cult classics for sci-fi. That's what I grew up watching because I was watching it right next to her. So I learned what the Borg was from Star Trek alongside with her. So it was pretty cool to see, like, just to see one of your parents kind of nerd out about it. And then for you to be like, okay, so yeah, that's cool too. Like, I could do that. But then also, like, kind of flexing the artistic side. It's okay. Well, I was always drawing on something, whether it was a wall, a sketch pad, the table, something, myself. I was always drawing on something. So, kind of the combination of the two came in college, where I double majored in fine arts and physics. So, which was pretty cool. Yeah. So I have a minor in fine arts, studio design. So that's basically like studying the modern art and post-impressionism era. So pretty much everything from Van Gogh, Degas through Picasso and Andy Warhol and Basquiat and Salvador Dali. So like I could probably write a thesis on modern art because I hyper fixated on modern art and just the style. But physics was kind of, also like a dual first love. So I was also questioning like why does this happen? Why can't we can see light and electromagnetism, but we can't see gravity, right? And what the heck's inside of a black hole? What is dark matter? Why is there so much freaking dark energy, but we can't see it? So like all of those things, I was like wondering, it's the mysterious part of physics, right? So that's what kind of captured me. And I saw some evidence of things like geometry and things like that in art. Cubism is one of those, right? Tessellations are one of those. So there's a bunch of elements of art that combine geometry, which now you have a math as a bridge between the physics and the art. So that's kind of like the origin story, if you will.
I think everybody has that real curiosity with an origin story. Speaking from experience, you can't be a strategic thinker as a physicist or a mathematician without having some sort of creativity. It's how are you
Right.
problem solving? And it's essentially bringing in that inspiration from one thing to the next.
Yeah. Yeah.
With looking for inspiration, where do you find inspiration and how do you think about
It's really nature. Gotta sit. If you're going to study nature, you got to sit in it. So I used to study outside, doing physics literally on the grass outside, and you doing your mechanics homework, whatever, but you're watching it in action, like a bird going through the air or dive bombing. You could even study gravity by a squirrel falling out of a tree and hitting the ground. Sorry, Mr. Squirrel, but thank you for teaching me Newton's mechanics. But it's things like that. It's like, okay, well, why did the squirrel fall faster than the leaf? So now you're studying air resistance. Now you're getting to know drag. Now you're learning friction. So it's all those things. You combine those together. It's like, yeah, you're going to learn physics really fast, but it's in a very intuitive way. And so you take that, there's a lot of things, that you can borrow from other areas of science and apply that back to physics. But you're using art as a language to then describe such things. You're using math as a language to describe it, right? So I like to tell people that math is kind of like a language to physics. If you know the math, you can talk physics. But just because you can speak the language doesn't mean you comprehend what you're saying. You got to know the science also. So if you combine all of that together, then yeah, you can solve a lot of problems in physics. And theoretical physics requires that creative brain because we have to constantly think outside the box and create new things. Test it, it's probably going to break 8 times out of 10. But it's those last 2 times. Oh, this worked, but the minus sign was wrong. Okay, do it again.
It's always that
It's
one
always the
minus
minus
sign
sign.
caught by reviewer too.
It's yeah. So it's very intuitive. It's a very cognitive kind of subfield, right? You got to learn how your brain works to do well in theoretical physics.
So this makes me question, does that bridge make us good storytellers?
I would say it could, provided now, caveat, not every theorist is a great communicator.
We know this.
Yeah.
We know this, but where your brain lives and where it belongs between the art and that intersection and beauty of the theory,
Mhm.
where's that all intersecting?
It makes for great storytelling. Yeah, like you said. So you have to be able to if I'm developing a theory, so let's take Einstein for an example. When he was
Sure.
developing relativity, this is 1905, he's on his bicycle riding in a circle. That's what he did. These were thought experiments, right? And so he would just think, no math, no papers, just think about the problem. Okay, well, how can I actually describe what I'm thinking? How do I describe this in such a way that's going to make sense on paper first? And so it's a technique that we use in theoretical physics or in some other sciences. You just run a thought experiment. Can I actually think this through? If I can't think it through elegantly, right, then I can't write it down elegantly. And that's something that Stephen Hawking kind of relied on too. So, and you can name a bunch of other theorists out there. Reva K. Williams did that. Paul Dirac was another one, but I'm bouncing between the decades, but these are a lot of theorists that I studied in their work that also thought, okay, if I can do this elegantly, if I can write this down elegantly and describe it, it's going to be a great theory. And so I think that's where the center of it all fits. The art, the physics, the cognitive part of it. It's all got to be rooted in, can you tell a great story with facts? If you can do that, then you have a great theory. All you need to do is have a bunch of money to prove it correct.
Hey, that is the big thing. It is
Right.
whether or not you have funding.
It's a big question. But, again, that's one of the other things that I love about theory. You don't need money to do pen and paper theory. You just need creativity and the skill set. And that's it.
When you're thinking about history, you see folks like Leonardo da Vinci, you see Escher, Islamic geometry. How do you see physics hiding in plain sight? You mentioned nature, but where else?
So the key word is patterns. If you can recognize the pattern, then you can recognize the geometry of the art in nature, right? An example is the honeycomb for honeybees, right? So their nest, they have a particular structure for the honeycomb, but we also see honeycomb lattices in other places in nature. The carbon molecule, carbon groups, you take 6 carbons together, it's going to make a honeycomb. It's going to be a hexagon, so not a pentagon, people, but it's very close, right? In terms of patterns, they do the same thing. Other areas of physics, we're talking keywords now. We're deep diving into things like topological insulators. We're talking
Right.
superconductivity. We're talking the quantum nature of physics and technologies today, right? So those are patterns. If we can figure out the pattern, then we can figure out the physics. But even before that, the inspiration comes from finding these things in nature. How is a snowflake? If you look at a snowflake under a microscope, you'll see the pattern. It's not just a little dusty ball falling out of the sky. It's a crystal. So it's things like that. And we know for a fact that particular molecules have very specific shapes down to like the single degree. And if you change that very slightly, it'll change the way the molecule works. So even those things, nature is very intentional. So there is a, however you want to describe a master creator, somebody was sketching this out and say, yeah, this is all going to work. And I'm going to click go on this nature machine. Yeah.
With that, do you think artists sometimes will recognize the mathematics before the science?
Sometimes they do. So, for example, Salvador Dali studied quantum mechanics before he painted the Persistence of Time painting. So, the Persistence of Time by Salvador Dali is what Dali thought quantum mechanics or quantum physics would be visualized as. So, the melting clock, all of these kind of abstract surrealism things, he borrowed from quantum mechanics and how it made him think, reshaped some of the patterns, reshaped concept, composition in the art. And so you can kind of see that, right? Cubism is another form of art that's kind of influenced by mathematics and geometry. There's a lot of, you can pluck out the golden ratio in most cubism paintings because they're using it to figure out the proportions of things. So cubism isn't exactly just random shapes in there. It is a very hard area of art to kind of paint in. It's a very hard style. But if you can get the shapes right, right? The geometry again was kind of influencing that. And there's many other areas of modern art, even contemporary art, that borrows from math or science. Math or science first will then influence the art that's created next. So it's kind of that pattern back and forth. And even some artists influenced the scientists. So there's another side to it, right? So
Precisely.
studying art will get you better science.
Now, will studying physics change the way you look at art from the past? Because I'm thinking about MC Escher and Jackson Pollock with some of their works, right? Jackson Pollock took paintings and a pendulum
Hmm.
when he had a brushstroke with his arm, and the patterns were repetitive so you could actually see that.
Yeah. So again, this is an analogy is to Jackson Pollock. It's like looking at phases of matter. You have solid is it's pretty structured. You know, a liquid is a little bit more fluid. A gas might look all random, right? But if you actually pay attention to the pattern, it's got something in there. It's something's repeating. So just like the Jackson Pollock, which I also studied, Jackson Pollock had a method kind of to his madness, I would say. It's not all just throwing paint on the canvas.
Right.
There was a method, a very structured method to creating that. It may look like chaos, but again, like a gas, an inert gas, it may look chaotic, but there's a pattern to it. So, and there's an area of mathematics called chaos theory that actually looks at this in very detailed fashion.
And some of that chaos theory and randomness in his work can actually now be calculated to see
Yeah.
and verify if it was him or not.
Hmm. Hmm.
Now, thinking about this a little bit more with structure, could you explain to us how physicists think of symmetry?
Boy.
Yep, I know. It's the loaded question.
Like I knew it was coming. So symmetry is basically you finding universal patterns, right? Just to lay down the definition of symmetry, that's what you're looking for when we're talking about symmetry in physics. On a deeper level, we are trying to get to like the real essence of why certain things work the way they do and why they don't. Why there's an asymmetry to matter, antimatter in the universe, and why we really don't want that to be equal. Otherwise, we go kapoof, right? So we're actually grateful that there's more matter than antimatter. Otherwise, you don't want the antimatter version of Ron. I don't think you want the supersymmetric version of Ron. But that is
Which
again,
version of the supersymmetric version of Ron?
and see, this is
Hey,
do not get me started on the multiverse of physics. But symmetry again is it can be used as a technique in physics to discovering new things. And so one of them being, discovering the fact that we have antimatter going in opposite directions in terms of scattering, spin, things like that. If you go back to the 1960s or 50s, right? You're going back to the Wu experiment, right? So there was experimental physicist, last name Wu. Her last name was Wu, and she did experiments using the decay of cobalt 60. So the cobalt 60 nucleus sent back particles instead of it sending it forward. And that is how we kind of had a first introduction to the weak nuclear force. So to discover, oh, there's other particles that are coming out of this thing other than electrons, neutrons, photons. We knew all those things. I'm like, cool. But You boson? Like, what the heck is that? So all of these experiments based on symmetry now, it is something that can discover new things, right? And so all in physics, we have a symmetry of charge, parity, which is handedness, left or right, right? That's your plus and minus sign, essentially. There's a time symmetry, there's translational symmetry. And so we're thinking about, okay, do I have things that move forward in time or backward, right? Do I have things that can only veer left or right? Are they only negative charge? There are some that are positive charge, right? So those are the fundamental laws of nature that we are figuring out. That's symmetry at its most fundamental level in physics. You can apply symmetry at home. If you put in your AA battery wrong, then your remote's not going to turn on. That is
Precisely.
symmetry. You need the charge to go in a specific direction. That's symmetry for it to work. Another prime example is if you cover your face with a sheet of paper, take a picture in the mirror, and then do the opposite, do the same thing. And then take each side and Photoshop them together, they will mismatch because the human face is not perfectly symmetric down the middle. And if it were, we would look weird. So
That's why I
there's
said, which symmetric version of Ron do you
right.
want?
So so there's so in essence, there's this beauty in symmetry that I really like in my work because my work involves not 3 dimensions of physics, but 4 or more. So we really heavily rely on symmetry, whether or not space is flowing in one direction or time in the other. That is symmetry in action. When you're studying black holes, you really need to learn symmetry to make sure that there's no rogue minus sign going somewhere, because otherwise you'll turn a black hole into a white hole, and that's no good.
Okay. So can you tell us like a little bit about your work?
Yeah. So
Because I'm
I
curious.
threw you right in.
You got to show the deeds, man.
So my work is I study black holes, but I am mostly interested in the effects of strong gravity on particle physics in high energy emission around a black hole. So we're talking near the event horizon, things like that, where the black hole itself, that is normally considered, if it's inside a galaxy, it's called an AGN, an active galactic nuclei. It's kind of the environment of the supermassive black hole at the center. So those are the objects that I study, but I also study the jets that come off of them. So you can think of a jet, relativistic jet coming off of a supermassive black hole as kind of like a black hole lighthouse. It's a stream of particles. They get accelerated from maybe 10% to 20% speed of light, all the way up to 99.99999% the speed of light. And all of those nines matter. So we're getting closer and closer. We can't exactly get to 100% speed of light, right? Because now we're breaking symmetries here. We're breaking some laws, but they accelerate extremely fast, extremely fast. We're trying to figure out why. Why are these jets created? Why are they in the shapes that they are over very long distances, parsecs in length? So that's on the order of 3,000 light years across. These are
Okay.
very large objects, and they're very bright. They're very energetic. They're very hot, and they come off very near the surface of a black hole, the event horizon, right? That area we call a photon sphere. We can maybe do another episode on black hole anatomy, but
We're going to have to. We're going to have to.
that is my work, and I look at the theory of synchrotron emission from these environments and the X-ray emission and some of the gamma rays. So I'm looking at the non-thermal emission. How was this influenced by gravity? Which you can actually see behind me, that's some of my work. It just got published like a month ago. So I am a pen and paper theorist.
Whenever I see your blackboard behind you, I'm going, what is he working on?
Right.
There's too many variables.
It's a lot. But I mean, if you were to peg it down to like one area of physics for those that are listening, if you want to study this is general relativity mixed with radiative transfer. So vector radiative transfer. So we're talking the transfer of radiation in curved space-time in 4 dimensions, not 3. Lots of math just to describe, just to tell the story. Yeah. So it's cool. It's fun to me. And I do computational work too, trying to learn more observational techniques. But it's a
That
lot of
stuff
coding, a lot of
comes with
math. Yeah,
time.
it does. Basically, if you were to take an elective, try to piece the different subfields of physics together, that's what you're studying. And I use a lot of Mathematica. Oh my Thank you, Stephen Wolfram, for inventing Mathematica and Fortran. So,
Okay. You're a
yeah,
Fortran
I am
guy.
a Fortran guy. Have been since undergrad. I've been using Fortran a lot. My advisor forced me to learn it.
Okay.
Thanks. And so
Thanks.
he was
Yeah.
like, "If you're gonna do real physics, you're gonna learn Fortran." I'm like, "You might be unhinged, but okay. I think you might be going somewhere here."
Not many people do, but have you also used Cobalt?
Yes, I've looked at some very old Cobalt code. I do not use it regularly. It's like no one uses Cobalt anymore.
Only government
Only
agencies.
government. It's only archaic codes that they can't get rid of. Some satellites are using Cobalt code. Yeah, we have some very old satellites that are still using Cobalt. Only because it's just the root code and you can't get rid of them. You can't get rid of the machine. You can't get rid of the server it's running on. Yeah. So
So, if anyone wants to learn physics, learn Fortran and Cobalt.
C and
Now,
Python's cool too. Yeah, yeah.
you learn them. They're applicable for things that are up to date.
Right.
Now, thinking about this in a different sense,
Mhm.
do you ever think about tessellations when you're going into your work? Because some stuff is a pattern within itself. And does that play into anything that you do for work?
It does in some sense. So there are, I would say there's certain techniques that we use to kind of make the math more computable on a computer. Obviously, we have to avoid 1 over 0. Can't calculate infinity still. But the other thing that we do is we kind of break down. This is a technique that we do use in numerical relativity. We break down our space-time, or we really it's called foliation. Basically, we separate the space and the time from each other,
Okay.
but in such a way that the physics is still doing the same, right? We call it a 3+1 split or foliation, where we're basically just separating the spatial components from your function or vector, tensor, what have you, your field, from the time component. And you're turning the crank on the math to compute everything numerically. In doing that, you have to develop a computational grid. All of you computational physicists out there, you know exactly what I'm talking about and the headache it is to get your grid and your resolution of the grid exactly the way you want it so that you can calculate things so that the end result, the data is smooth, right? You don't want any hiccups or anything like that. You know exactly what I'm talking about. Smooth
Yes.
data is great data. So that is one area that we kind of use. We're very closely matched to like tessellations. And tessellations are just repeated patterns, right? Over a large scale. Another area of physics where you'll see that is things that are more statistical in nature. So if you've ever run a Monte Carlo simulation, you are using tessellations. My God.
I do not envy people who have to do that.
I have my love-hate relationship with the MCMC, and that's Markov chain Monte Carlo, just so we're clear.
You beat me to saying that.
Okay.
As an industrial engineer who started her research in soft condensed matter physics.
Boy.
Yeah,
Yeah.
I have some
Huh.
strong feelings about
Strong.
MCMC.
Very strong.
Yep.
But it's very powerful too. It's a powerful tool. It borrows, well, the icing model for our condensed matter people or material science people who do that also borrows from this is your nearest neighbor approximation. So again, they use these techniques. It's not just exclusive to physics. It's used in economics very heavily.
The other thing that I think of was one of the things that I worked on is folding and packing.
Yeah.
And you're looking at various lattice shapes and think of it as origami,
Mhm.
even
Mhm.
including the satellites and some of the space stations, whether that's going into like radial symmetry, whether that's a Muria map folds, and you're also taking the packing and changing not just the structure, but also the materials
Yeah. Yeah.
that you're using. So, to break it down for people in normal terms, if you can fold a map, you can fold a satellite. And some of this is with a hinge, other times it's squishy contact lens material.
Mhm.
And
Mhm.
your properties in bending and folding are different. And it just changes that.
Yeah, it's very it might seem like a simple problem, but one thing that and people saw this live, it was James Webb Space Telescope.
Yes.
Unfolding the universe, that's where it came from. The telescope had to literally be folded up, shipped out, right? From it launched from the French Guiana, and they had to unfold it in orbit, in space, and then push it out, right, to its Lagrange point where it's at now. Just doing phenomenal work. But the engineers that designed it were just out of this world. They took a grand problem. Shout out to all of them. It's yeah, it's awesome. One of my good friends, Jane Rigby, she's phenomenal. Like it was there were just and there were just so many science and technology champions on that team that got it up. It was amazing. So shout out to all of them. Hi Jane, if you're watching this.
Have you ever thought about underlying lattice structures, whether that's in your paintings, whether that's in some jets, whether that's in some cosmic events? I know you do
Yeah.
a wide array of art, and it's super cool.
Yeah, it is a tessellation actually is a it's a technique in the art world. It's a way that you can ensure that a pattern is created the same way every time. Stenciling is essentially a kind of hard and fast version of tessellation. That's kind of where it started, stenciling, and they used print work. So back in the 60s when they kind of revolutionized print work, this is how they did it. They made one stencil, you put it up on a canvas or your artwork, and then you repeated it. You just keep repeating the pattern. So Keith Haring was an artist that I can think of. Whenever you see a Keith Haring painting or design, that's a tessellation.
Okay.
And so, yeah, and that's another. It's kind of his work is becoming very prominent now in the contemporary world. Andy Warhol was another pop artist that did tessellations or print work. And so it's these print work is now it's coming up, right? You can have a screen printer on a T-shirt that will utilize tessellations. So in my work, I look at and I borrow things from lattice structures. I borrow things from okay, well, how if I'm making a wave, can I put nodes in this wave or design and make it kind of structured more like a graph, right? So now we're getting borrowing things from like graph theory, group theory, and things like that. Lattice theory. I mean, you name it, there is a artistic rendition of it when considering tessellations and things like that.
Now, is there any point that you've ever come across where too much structure has ever become limiting?
Yeah. And this is why minimalistic art is so dynamic because you can and this is what we in the art world all of our artists will know, you can overwork a painting, you can overwork a composition where you're just trying to squish in too much into the composition. If you take a lot out, sometimes it makes a much better painting or design. And so in the engineering and science world, we call that optimization. In the art world, we just call it minimalistic. So that's something, and minimalism is a big area of art. Can't think of any minimalistic arts off the top of my head. But there is another area that's more minimalistic and geometric in nature. We called that neoplasticism. So it was a movement in art. Another one that came right before that was the Bauhaus movement that came out of Germany. And we know Bauhaus because we know the art and we know the furniture
Yes.
that borrows from that minimalistic mid-century modern design. So now we're thinking Frank Lloyd Wright and the way he designed the mid-century modern home and furniture and things like that. So you can look at these things and they are very minimalistic in nature, but they are very structured and the design is sound. The design is strong. So you don't need a lot to have a great design. The same thing with physics. You don't need a lot. You don't have to cram a bunch of things in there to make an elegant theory, to make a beautiful theory. You actually need it to be simple. If you can describe it simply, then you know it well. So that's the power kind of in minimalism for physics and some art.
Minimalism, not just only in physics, art,
Yeah.
storytelling, a lot of attorneys. The less that you
Yeah.
say,
It's and you had to get I mean, so I think it's safe to say, like, I grew up in the early times of Twitter. We only had like 140 characters. So you had to get we didn't have 250. Like, what is that?
well, yeah, we don't have
No,
unlimited
we don't
characters
have
to unlock
unlimited.
a novel.
But we had even less. Social media was archaic. We had a finite amount of characters that you had to describe your little thing in, your picture, your video, whatever. And we weren't really monetizing it like crazy like we are today. But we didn't have threads. We had to really make a concise statement on what we were trying to say. And I think it taught us how to talk, right? So it kind of taught us minimalistically, if you're not abbreviating a bunch of things, it kind of teaches you how to talk very concisely if you're using it for that. There are other things that we use for social media that's not conducive to any of our work.
We don't need brain rotting.
We don't. We don't
We
need that.
don't. I think that there's been a fine line in that technology. Are we the last generation? I'm going to date some of us here. Actually, the both of us here. Are we like the end of that generation that knows how to use a rotary phone?
Oh my, I think we are. But it's yeah, we grew up with the brick. The cell phone was like this big, and half of that was the battery, not even the actual phone. And now we have iPhones that are just it's ridiculous. It's
Yep.
yeah. So we've seen it all.
We got our cute pink razor phone that I still have
Do not get me
somewhere.
started on dial-up internet. For the love of God, I was so glad. So glad we don't use dial-up anymore.
They just got rid of the last AOL
Yeah,
dial-up. Yep, that's a classic sound.
it's amazing.
When you're building out models, whether it's black holes or gravitational waves, do those things feel artistic at all?
In a sense, yeah, because you can't just kind of design a model, compute your results, and put up a white and black graph, with a bunch of lines saying, "Yeah, this is a black hole." Okay, it might be, but my equations were actually computed in 3 and 4 dimensions, not a 2D graph. So a 2D graph doesn't really give me, okay, well, where are these photons going? I
Right.
see the peaks, but where how are they traveling around a black hole or something like that? How is the magnetic field manipulating this trajectory? What's the shape of that? So when you're studying these objects, jets and black holes, even accretion disks that are around a black hole, you are really talking about geometry. Geometry plays a large influence on some of these mechanisms. And so if we're going back to how do I display these results after I compute something, that is in the realm of scientific visualization. And that's a big deal. NASA has a scientific visualization studio. It's called NASA SVS. Bunch of great and free graphics that you can download and use. Give them credit. They're awesome. But as far as, how do I display a jet? How do I describe a black hole visually? You need color. You need the proper geometry. Black holes are not perfect spheres. They're oblate spheroids. They're squished because they spin around. If I was to calculate the volume of a jet, is it a cylinder or is it a cone? Um, a lot of the times when you see high energy astrophysics data, right? You're not looking at a Hubble type picture, Hubble's in the UV and the visual or the visible spectrum. We're not looking at radio, X-ray, gamma, right? So
Right.
those things are they're invisible to the human eye, but we use what's called false color images to kind of
Okay.
colorize some of these objects viewed in these particular bands. So generally you might use blues and purples for X-rays,
Sure.
greens, for gamma radiation, and then maybe red or something yellow for radio data.
Okay.
And if I put them all over top of each other, then I'll see a rainbow of things. I'll see a rainbow of data and I can then pluck out. Well, that's where a high cluster of the X-ray knot was. I had an X-ray flare there because I know I colored my data purple for X-ray. So I can then go back after I've created this image and then reanalyze the image to see, all right, now that I've colored everything, how does it all relate? So that goes into the visualization process. It goes into analyzing the data that you either observe or compute. But then also, it goes into, again, telling the story of your science. If you have very good visualization that's based on data, you can tell a great story. And that now removes a lot of the back log or the backstory, right? The filler, the jargon that you have to explain to say, well, a black hole is not a sphere. Well, I can just show it to you instead of just tell you. I can let you
Right.
figure that out now. And now you're discovering for yourself that a black hole is an oblate spheroid and not just a sphere because you can see it, right? It's those things. And it makes for a very good teaching mechanism, also, especially when you're
Okay.
talking to the general public.
That is super neat. So, just thinking about that, would that even, if I was breaking it down, would even some of that look like level curves on a graph?
Yeah.
if you were doing it topologically and I was cutting something on a map down. That was the first thing that just came to my mind.
Yeah, and you've have probably the everyday person has probably seen it. If you looked at your GPS, Apple Maps, it's a level set, right?
Okay.
So it's calculating some height, some distance, and it's giving you a map. Cartography originated that, right? So if you're looking at the surface of the ocean, waves and things like that, that's how they map it. That's how we map surfaces of planets, the moon. I mean, you name the area, there is some type of surface visualization associated with it. And mathematically, we'll call that a level set. I have some constant value at each surface, right? So visualizing ocean depth is another example of level sets. And so it is a classic and widely used technique when you're visualizing scientific data.
Now, let's shift this a little bit more to gravitational waves.
Mhm.
When you're thinking about this, just waves in general, we're thinking about them visually, geometrically. Some people might think of that as like musically,
Yeah,
if that gives you something for a perspective for a mental visualization. How did those things really appear for you, whether it's in art or in your mind? And when explaining them to people who've never seen a diagram before, what metaphors would work?
sound.
Okay.
So it is literally the way sound waves are created in air, the way we're talking through the microphone and, it's vibrating some, node inside the microphone is a magnet. It's propagating the sound, turning into electrical signal. That is the same way that we study gravitational waves. We look at the literal vibration of space-time and its effect on something like a laser. So they use laser interferometry to detect the passing of a gravitational wave, and it's on the order of like picometers. It's like 10 to the minus 15, much smaller than that. A gravitational wave amplitude is on the order of like 10 to the minus 21, 23. So these are extremely small vibrations that we're detecting. But
Okay.
if we can detect the data, right, then I can transform that or I can sonify that, right? Sonification is transforming the data into sound. Then I can actually create an orchestra of gravitational waves. Right, and so we've done that before, and when LIGO first came out with its observations in, 2015, I was in grad school, and I freaked out. I'm like, "Yo, this is" it was like I'm not gonna say it was a tinfoil hat moment, but it was like, "Oh, the universe is actually talking to us." It's like, "Great, we don't have anything to listen to it." Well, we have LIGO. It's like, "Okay, but we just have 1 detection." It's like, "What are we gonna do with it?" I don't know. We're gonna do it again.
We're going to do it again
We're gonna
and
do it
make
again,
sure that there is some sort of art or essential tool
right?
to make people feel space time.
So it is a very kind of it's very intentional in terms of matching it back to sound, and which is another one of your senses, right? So not just the visual art, but now you can kind of hear the data. You can look up chirp mass sound on Google, and
Okay.
you'll hear the gravitational wave go by, and it'll sound like a little whip. It'll just literally sound like whoop. That's the chirp mass. So that little spike at the very end is the two black holes spinning around each other, combining together until they begin to overlap, and that's the chirp mass. So that's that
Okay.
little blip in there. It's a very fast signal, so it's only on the order of like maybe a few seconds, but the universe is talking to us
That is
through
super cool.
gravitational waves. Yeah, it's really cool.
So, you told me before this interview that you're launching a new course.
I
Tell
am.
us about it and what are you hoping people walk away from it?
On if you've already signed up, I'm behind, so more delays coming, but don't tell anybody.
Don't tell.
But the source, the course, it's called The Artistic Journey into Physics, and it is combining science and art together. But I'm doing it in such a way that it's not disconnected. A lot of the times, whenever, and I've seen this done before, nothing against them, but I had issues, and I thought, well, you could have introduced this and combined it this way. And so the course is set up into 3 different tracks, with each track increasing in kind of mathematical or physics difficulty. And so the course, by its fundamentally, it's combining concepts from modern art in our traditional elements of design now. So you arts majors, you'll see the elements of design in there: shape, space, frequency, there's momentum, there's color theory in there, things like that. And so one of the examples is, okay, well, you can relate color theory. Red and green are complementary colors, blue and orange, purple and yellow. If I combine red and green together, I get brown. Blue and yellow make green and things like that. So that can be related back to light and the electromagnetic spectrum, visible light, optics, things like that. They really rely on some of the same concepts that we use in color theory. So combining those two together now brings a more intuitive kind of thought process into how physics and art, or nature and physics, nature and art combine together. And this is really where I'm really revealing some of like the secrets and how some of these people thought, because this is what's going through our brains for the theorists, right, in physics, who are also artists. Einstein played the violin, Feynman played the saxophone. I paint. I also played the clarinet for a number of years, actually since I was 8, clarinet and piano. So it's this, you'll be surprised at how many hardcore scientists are also artists at the same time. We're using the
Yes.
same parts of our brain. So that is where the course kind of borrows from. And these 3 tracks, I will say, track 1 is an atomic apprentice, where it's a basic concepts in physics. This is the explain it to me like I'm 5 track. And I literally put in there. This one's if that's what you're looking for, this is for you. This is for you. So very little math. It's more conceptual, more fun, very visual. I'm going to be introducing some kind of hands-on things that you can do, some maybe a scavenger hunt or 2 in there. So you can also find, okay, well, what is he talking about? Patterns in nature. I don't see these. Well, look at a seashell and then come back to me. You'll see the patterns.
Look at
Look
a
at a snail,
sunflower.
a
Look at a
sunflower.
fern.
Burn. You'll see fractals everywhere. Yeah. So you'll see it. Track 2 is more math, a little bit, going kind of deeper into the concept of the physical laws of nature, and that's the cosmic artist. You can kind of see the pattern here. You're an atomic apprentice, you're a cosmic artist. And so if you are, like STEM creator on social media, if you're an influencer, or if you're a motivated middle school, high school student, track 2 is for you. Right. So, and I list kind of prerequisites. The first one, you just need a desire to learn. The second one, you're going to need some algebra, some trigonometry, a little bit of motivation, so you can kind of get through it. The third track is going to be introduced. I'm going to really reserve that to like a private cohort of students or people interested, and that's the relativistic surrealist. So that is going to be hardcore physics. This is now.
Is there a level that people should think about?
You definitely have to know. Definitely gotta go calculus, differential equations. This is for the physics majors. This is for the math majors, undergrad and grad,
Engineers.
engineers. If you're a STEM major and you've already had calculus, yeah, you'll be able to figure this out. But it's also for your advanced enthusiast also. So if you're well read and you can handle it, you can apply to be in that cohort, and I'll review whether or not, you know, you'll be ready for the hardcore theoretical physics.
The
Some say they
professor
are.
is in.
Some say they're ready. It's like, okay, here. Now, here's a field equation. Can you find me the eigenvalues so I can actually pluck out the nominal modes for the field? It's like, what is that? You're not ready. that's the level it's gonna be at.
Grad students ask me that question, okay? So
It's gonna be, I mean, yeah, at a bare minimum, you need to at least have physics 1 and 2, modern physics, some vector calculus.
linear algebra.
Linear algebra would be nice, some coding, Fortran C, something like that. Mathematica is awesome.
Python.
Python, you could still do Python.
You've got a bias to Python? I see that facial expression.
Because some people, they swear by using Python for parallel computing.
No.
And I'm like, yeah, that's only so that we can organize the script, not to actually do the computations on the arrays. You need C or Fortran to do that. A compiled language, not a scripted one. We got to get out of the notion that Python's a silver bullet for everything. It's
I
great.
agree.
It's a great scripting language, and it does a lot of cool things. Hard if you wanna compute math, you're gonna need Fortran or C to do that, and a lot of
I mean,
patience.
you can even do it in Mathematica, but you're gonna be banging your head against the wall.
You gotta there's a learning curve for Mathematica, but once you get it, it's pretty tough. It is aw Mathematica is awesome, but
Yup.
the track 3 is really for really teaching you hardcore how to think like a theoretical physicist now. How do I where did Einstein's equations come from? We're gonna at least touch on a very abstract view of that. How do I get Einstein's field equation? Where does that come from? How do I prove that? How do I derive it? And things like that. The Feynman lectures, probably touch on those. And so it's gonna be a it's not an extensive course because again, my time is everywhere. My calendar is ridiculous.
You're doing
But it
everything but the kitchen sink.
listen, so it's I was thinking of putting all of the lectures or whatever out there at one time, but I've moved to, okay, I'm gonna do this like I'm gonna push out one every 2 weeks or 3 weeks or so, stretch it out a little bit. It gives you more time to consume the material, and to really kind of follow along and anticipate and, okay, well, what's coming up next?
Yup.
Yeah, so it's
I
gonna be
know
really
that
cool.
feeling.
Yeah. So you can sign up now. You can go to journeyintophysics.com and sign up to be on the wait list. It's awesome. I'm excited for it. It's gonna be cool.
Wonderful. I have one last question for you. Do you think art makes you a better physicist or being a physicist makes you a better artist?
Ooh, that's a good question. I think art makes you a better physicist because there's no real well, there is some real I would say hard and fast rules to art, but you are the essence of art. You're learning, you're teaching your brain how to create. That's the essence of art. But you're not only teaching it how to create, you're teaching it how to re-describe what you've already seen or imagined. So there's a large creative imagination process that you have to learn how to do. You got to train your brain how to do in art. Physics, you don't have to do that. But if you can do that, that's a game changer because now you're not just imagining things, but you're imagining a solution to a problem. You're a problem solver now. And we've known, we all know, if you can create and get creative in solving problems, then you're doing a great job in figuring some things out. Out of the box, forget the box.
Forget
Draw
the
a new
box.
box. Just draw a circle, a triangle, whatever it is. Maybe the solution requires you to color everything outside the box, but nothing inside the box.
What was the saying? Someone said, "Well, I don't have a box. I don't have a chair. I found a piece of paper and folded it myself."
Right.
I'm like, "So look, there's another piece of paper. I'm just going to go and fold it." And someone's like, "What?" I'm like, "Yeah, it only took me 3,000 pieces.
Yeah, that's it. Yeah.
That's all. That's all. But it's structurally stable and holds my weight."
Exactly. Exactly.
But on that note, thank you so much for coming on the show, Ron.
This is great. Thanks for
This
having
was
me. This was
great.
awesome.
This
I
was
think we had a great
awesome.
time.
That's all for today's episode of Breaking Math. If you've enjoyed this conversation, share it with someone who loves science, art, or asking big questions that don't fit neatly into one box. You can find the links to our show and to Ron's work, his course, and everything else we've discussed in the show notes. As always, thank you for listening, being curious, and for noticing the patterns in the world around us. Until next time, stay curious and stay informed.